So welcome everybody to the virtual condensed matter seminar. Today we're happy to have Hlynur Gretarsson visiting us all the way from northern Germany from the DESY photon source. Hlynur got his PhD after 5 years of working in the center of a windowless basement alongside myself at University of Toronto. Where he did some really pioneering work using resonant inelastic X-ray scattering to look at honeycomb iridates, which at the time were just being proposed as the first Kitaev-model compounds. After that, he moved on to the Max Planck Institute, working in Bernard Keimer's solid-state spectroscopy group, where he did a lot more nice resonant inelastic X-ray scattering, as well as some Raman scattering, looking at iridate and cuprate materials. And then after that, he's now moved on and taken on kind of a monumentally difficult task of building a new resonant inelastic X-ray scattering spectrometer, which I think he's going to tell us a little bit about. The spectrometer is special in that it works, I guess, in this tender X-ray regime. Maybe you don't like to call it tender, but it's an X-ray regime that had not been accessible until Hlynur built this beamline. Welcome, Hlynur. Looking forward to your talk.
Yeah, thank you, Kemp, for this introduction. So I'm going to be spending the next, I think, about 50 minutes talking about unconventional magnetism in Ruthenates. And just like Kemp was saying, I'm going to be using, or most of the results are actually coming from a technique called RIXS. And to get these results, we built an instrument at Petra 3, which is a synchrotron at DESY, to look at this excitonic or Kitaev-like magnetism in Ruthenates. So I did my postdoc with the group of Bernard Keimer in the Max Planck Institute of Stuttgart, and I still keep contact with them. They are actually a big sponsor of this RIXS project. And yeah, so without their support, this would not have really been possible. Okay, so the talk is going to be split into 4 parts. I'm going to introduce to you briefly the Excitonic and Kitaev models, which we are going to look into more details. I'm then going to show you a few slides on the RIXS project, which is this beamline that we're using to measure magnetism in Ruthenates, and hopefully convince you that this was actually a very good idea. I'm then going to spend most of the talk discussing 2 families of Ruthenates, the Perovskites and the honeycomb, which we believe belong to this excitonic and Kitaev class of materials. Okay, so let's just start with the excitonic magnetism. And I find it actually easy to take a step back here and think of what happens when you have spin 1/2, 2 sides that are actually in close proximity to each other. And then typically, what happens is you get a singlet ground state. This is non-magnetic. And then at a higher energy, you can get a triplet, which is S = 1. Now, the gap between singlet and triplet can be adjusted with magnetic field. And then at some point, you can actually lower one of those triplet states, either below the non-magnetic state or in close proximity to it. And when that happens, your ground state can actually change. And you can imagine being in a scenario where you have some kind of mixing or different weights between the triplet and the singlet. And so what's interesting in this case is that magnetic moment is actually soft. So it's not rigid. It doesn't just change in direction, but also can change in magnitude. And this is the kind of new magnetism that we are looking for. It's been realized in real system. This was a good case on thallium copper trichloride. This is work that was done more than 10 years ago. But this was realized using a dimer system. So you have these copper spin 1/2 dimers shown here in the ellipse. And then by applying pressure, you can actually cause some of those sites to transform or switch from a singlet into a triplet. And then these triplet sites can actually talk to each other. And then at some point, this nominally non-magnetic compound actually develops long-range order. But before it does that, you have this new kind of magnetism appearing, which is that you have you will get a transverse magnon and also a longitudinal mode. Okay, so how does this actually link to us? Well, we want to realize this kind of model on a single site, so not using dimers. And there was a theoretical work in our group by Kitaev showing that if you have a spin-1 system, and also if you include spin-orbit coupling, then you can get this kind of singlet-triplet physics on a single site. Okay, so that's it for the excitonic model for a moment. The other model that we would like to discuss is the Kitaev model, and I think this is something that you are probably more familiar with. It is based on having spin 1/2 on a honeycomb lattice. That is coupling very anisotropically to the nearest neighbors, meaning that different links are coupling to different spin components on your site. And so this model will actually not have any long-range magnetic order. In fact, you will. It's actually been predicted and shown that this is going to be a quantum spin liquid. So this was in 2006. There was another groundbreaking work in 2009 by, again, our theoretical group, which is Kitaev and at that time George, showing that the Kitaev model can actually be realized on a honeycomb lattice if you have a spin 1/2, and spin orbit coupling together. And I think it was interesting that in this paper, they actually even pointed out what kind of materials you should grow to get this kind of physics. And this was sodium 2 iridium 3 that was later grown and discussed in the realms of the Kitaev model. Okay, so the theme here is that you do seem to have the correct valence and spin orbit coupling to get this kind of unconventional magnetism. So this brings me to Ruthenates. So it is obviously well known that if you go in towards the heavier elements, spin orbit coupling is going to be strong. So that's a good way to actually try to realize these kind of models. But if you go too heavy, so towards maybe the 5D, then you also have to take into account that correlations become weaker, which means that you're less likely to form these important local moments. So we think there's a good compromise in going towards Ruthenates. I mean, they show a variety of valences. And there are very important X-ray spectroscopy experiments that have shown that spin orbit coupling is actually influencing the ground state. And the first one was actually done on a D4 system. This is calcium-2 ruthenium-04, which we're going to be talking about later in the talk. This was shown in 2001 by using oxygen K-edge X-ray absorption spectroscopy that had a very large temperature dependence, which was taken as a sign that the orbitals and spins are talking together, so spin-orbit coupling. The other important experiment that was done 13 years later was done by our colleague here, Kemp, on a D5 system, honeycomb, this alpha ruthenium trichloride. And in that paper, Kemp used ruthenium L3, L2 X-ray absorption spectroscopy. He looked at the ratio between these absorption lines and found that that was actually larger than 2. And that's also a sign that spin-orbit coupling is influencing or determining their ground state. So these are kind of the key experiments that we are following and show us that here are two good candidates for this kind of unconventional magnetism. Now, Ruthenates are not the only ones that are promising. There are, of course, a lot of activities in iridates. And like Kemp said at the beginning, this is something that I did during my PhD, which were the honeycomb iridates. And then I think something interesting is happening these days, which is that it's possible to get Kitaev-like magnetism in cobaltates. So you can see this is not only centered around 4D, there are also 3D and 5D. Okay, so to look at magnetism in Ruthenates, we are going to be using resonant inelastic X-ray scattering. It's normally just referred to as RIXS. So in a RIXS experiment, you put your sample into the beam of photon or X-rays, and you tune your incoming X-rays to an absorption edge. So this is the resonant effect. And what happens then is that a core level is going to absorb the photon and then promote an electron up to the valence band. And then typically a different photon is going to fall down, and it's going to emit a different electron is going to fall down, emitting a different photon out. So in reality, you build an instrument that can give you a very narrow bandwidth that comes in, because the narrower the bandwidth is, the easier it is for you to identify energy losses. And then you build a spectrometer that can tell you at what angle the photon came out and what was the energy. And if you just use then conservation of momentum and energy, then you can easily figure out what kind of excitation happened in your system. So what is it that we are seeing with RIXS? Well, we can see excitations ranging from high energy charge transfer all the way to phonons or even superconducting gap, like the ones in cuprates. What we are interested in, and what I'm going to be talking about for the rest of the talk is actually the orbital excitations, sometimes also referred to as DD, and then magnetic excitations, spin waves. And you have to keep in mind that X-rays carry significant momentum. This is obviously more than visible light. And so you can transfer that momentum to your excitations. And in some cases, the magnetic excitations are going to disperse, forming a magnon, or the orbital ones are going to form an orbiton. And then based on this dispersion relation, you can actually extract a very useful coupling constants that tell you about the ground state of the compounds. So the message here, though, is that RIXS is simply just giving you information into the dynamical structure factor in a similar way to what inelastic neutron scattering can do. Okay, so history has really shown us that if you want to look at magnetism in transition metal compounds, then you're best off using the L3 edges. So if we stick to the examples that I presented before, cobalt, ruthenium, and iridium, then these L3 edges actually correspond then to 2B, to 3D, 4D, and 5D. And they actually cover a large energy range. So cobalt would be below 1 keV. So this is categorized as being soft X-rays. Iridium would be in the hard X-ray regime. And ruthenium is in a regime that is called tender. And it's really no man's land. This is where synchrotrons tend to avoid. So there's 2 to 4 keV. Now there's a problem here, because it's actually quite easy to go towards a soft RIXS beamline or hard RIXS beamline. It's very established how to monochromatize X-rays or build a spectrometer. For soft X-ray, it's based on grading, which means that it's just like a prism. So different energies will have different takeoff angle. So further you go, the easier it is for you to distinguish the energies. Crystals for hard X-rays are a little bit simpler. They just take broad bandwidth and only reflect a narrow energy range out of that. So the reason there have been no tender RIXS beamlines built is because neither grading nor crystals work particularly well at the ruthenium L3 edge, for instance, which is at 2.8 keV. And there's also not a lot of effort in building an instrument like this. So I like to present this statistic, which is just going on Google Scholar and looking at soft, tender, or hard X-rays. So you can see there's an order of magnitude. So we were determined to try to fix this and build a tender RIXS beamline. And before we decided on what kind of concept to use, I think it's important to show you that this decision is actually quite important. And the reason for that is those beamlines look fundamentally different. So if you look at a typical hard X-ray RIXS beamline, so this is a state-of-the-art beamline at ID 20 at ESRF, you can see that the spectrometer is quite compact. It's 1 meter, it can be 2 meters sometimes. But this has to do with the fact that crystals just act as band filters. They select a particular energy and diffract it. If you go for the soft X-rays, then you end up with this, order of magnitude larger spectrometer. And that is simply just because you want to be able to identify or distinguish different energies more easily, right? They disperse more. Okay, so our decision was actually to go with the crystal optics when we built this. There are various reasons. One is also that it's less of a construction, as you can see here from the pictures. There are other reasons as well. So here's our instrument. It is located at beamline PO1 at Petra 3 at DESY. It's called RIXS, which stands for Intermediate X-ray Energy RIXS. Intermediate is also sometimes just referred to as tender. Okay, and I will use tender for the remaining of the talk. If you want to read more about the instrument, it has been published last year. But in short, what this instrument does is that it takes a broad bandwidth coming in. It's like 1 eV, and then it strips away most of the photons and leaves you with a narrow bandwidth. And remember, in this RIXS cartoon that I showed you before, you want to have a narrow bandwidth coming in. We can use focusing optics, and this is a great advantage of X-rays. So you can focus the beam down to, like in our case, 10 by 10 micron. So you can work with very small samples. And the spectrometer is this compact thing here. It's only 1 meter and works in this roll-on geometry. So we're quite proud of our instrument. We've been able to push the resolution all the way down to 76 millielectron volt. And just to give you some reference, if you want to look at the copper L3-edge or iridium L3-edge, then this resolution is what I would say a factor of 2 worse than what you can get at the other instruments. So we've done quite a good job here. There's also another thing to keep in mind with tender X-rays, and that is that because we are at the relatively high energy, you can transfer momentum that can go beyond your first brilliance zone. And this is something that is not given when you work with soft X-ray RIXS. So for instance, in cuprates, you cannot go towards the magnetic Bragg peak. Okay, so let me now show you an example that our instrument works. So one of the first cases we looked at, and this is not part of this unconventional magnetism. We had a quantum magnet, strontium, ruthenium-2, oxygen-6. And this was an interesting case to look at in the beginning. It has a honeycomblattice, as you can see here in plane. It has a magnetic order that is antiferromagnetic, spins are pointing up or down. And what caught our attention with this compound was the fact that the needle temperature is extremely high, almost 600 Kelvin. So we thought perhaps the interaction or the exchanges between neighboring spin must have been quite high. And if it's high, then it's easier for us to see it with RIXS. It disperses towards higher energy. Now, the other thing that came kind of as a bonus was the fact that it's very hard to grow large single crystals of this compound. And the largest one is about 50 micron. And that meant that no one really knew how the spin wave would look in this system, because if you want to use, for instance, neutrons, you have to co-align a lot of them. And this seems just impractical. So this is our data here. What I'm showing you is the energy loss. RIXS energy loss is a function of momentum. And just like in the cartoon before, you have these high energy DT excitations, orbital excitation. Here's a gap. So there's nothing happening in the system. Everything, the charge degrees of freedom are frozen. And then you have the magnon appearing. Here's the magnetic Bragg peak. And then it disperses towards the highest energy here, almost 200 MeV, and then goes back towards 0 at gamma. We were able to fit the spin wave with a simple Heisenberg model. And indeed, we find that the exchanges are kind of large, almost 70 MeV. But what we believe is the reason for this high needle temperature, or why the magnetic order simply doesn't want to melt away, is the fact that there's a gap. So there's a gap here and here that is about 35 millielectron volt, and that kind of coincides with this temperature scale, 600 Kelvin. And this is coming from this term here, K, this anisotropy that is coming from, we believe, spin-orbit coupling. Okay, but this was kind of vague in the paper. The point is there's a gap that we can see that is causing the robust magnetism. Okay,
Hlynur,
so
can I ask a question?
Sure, go
Is
ahead.
it what is it spin half?
It's spin 3/2.
Okay, thanks.
Okay, so I think I've now shown you, hopefully convinced you that this instrument is capable of measuring magnons. And this was actually taken with a resolution that was 150 MeV. So we've improved it by a factor of 2 since then. Okay, so what I'm going to be discussing now are the perovskites, so calcium-214 and the bilayer version. And most of these results have been published quite recently, but I'm also going to show you some data that is being prepared for publication. Okay, so I mentioned to you in the beginning that we are interested in looking at the excitonic model on a single site. And to do that, we've just followed the instructions by Kitaev, which is that we need a D4 material that is, in this case, in a perovskite, for instance, which has spin-orbit coupling. As you can imagine here being 4 electrons, spin 1 system, you add to that the orbital moment, which is L equals 1, and you get J 2, 1, and 0. So this is your singlet here, and here is your triplet. And the gap between the singlet and triplet is actually determined by spin-orbit coupling. So this is where you might actually not want to have a very large spin-orbit coupling like in the iridates, because this would be fairly large. So the key to reach the excitonic model is actually to be able to apply some perturbation. In this case, you can do tetragonal distortions to your system. And what can happen is that, just like in the beginning, you have some of the triplets go down, and at some point when the gap between the singlet and triplet becomes less than the exchanges between the moments, the triplet will actually condensate, and you will form a magnetic order in your system. Okay, so this is what we want to try to find. And the candidate, our prime candidate, is this calcium-214. I showed you also in the beginning that there were evidence that spin-orbit coupling was in the system. So this seems like a good start. So here's the crystal structure. It has antiferromagnetic order in the plane, as you can see here. The moment is somewhat smaller than what you would expect for spin 1, which would be 2 Bohr magnetons. So this is only 1.3. Now, this system is extremely sensitive towards dimensionality. So if you go from the single layer to the bilayer, what happens is that this antiferromagnetic order in the plane becomes ferromagnetic. The moment also shoots up to almost 2, which is what you expect. And you get this, the bilayers are actually antiferromagnetically coupled. If you decide to add a little bit of titanium into the system, this is 1%, this tiny bit, titanium is non-magnetic, and then you recover this antiferromagnetic order in the plane, and you get also this reduced moment. So it's quite sensitive, and this looks like a good system to be studying. Now, if you look at transport measurements, then calcium-214 has a metal insulated transition at 360 Kelvin. Then nothing happens for almost 250 Kelvin until at 110 it becomes magnetically ordered. If you look at 3 to 7, it's actually metallic for its entire temperature range. But then when you add this titanium and you change the magnetic structure, then it becomes an insulator, so similar to 214. If you look at susceptibility, then 3 to 7 has 2 transitions around 50 Kelvin. The first one is the magnetic order. The second one is slightly different magnetic order, and then some small changes in transport as well. we do this titanium doping, then this becomes a single transition and very sharp. And this is what I find actually quite interesting. So you add some dopant to your system and transition becomes even sharper. So typically you wash things out with doping. Okay, so 214 is actually some system that we've been studying in Keimer's group for some time. Some of our biggest results came from inelastic neutron scattering measurements in 2017. And remember, we're here trying to find evidence for this, soft moment. And here is theoretical calculations of the magnon dispersion in the system. You have here the magnetic Bragg peak, so at 1,0. This is a transverse wave, which is shown here. This is the moment changing direction. But we also have this longitudinal mode, which is the moment where the moments are changing in amplitude. And this is the new thing that appears only when you have mixing of the singlet and triplet. Now, this calculation is of course supported by experiment. And here is, for instance, data taken at the gamma point, where you can see the transverse and longitudinal mode appearing. You can also use, what's interesting here in the spin wave dispersion is the fact that this is not a Heisenberg model. It has a very large gap at gamma that is coming from this anisotropic term E here. Okay, and E is actually, and this is something important, E is proportional to tetragonal distortion. 214 is actually quite distorted. So the octahedra are squeezed. You can see evidence for soft magnetism also with Raman. And what I'm showing you here are the Raman modes, the phonon modes in the AG symmetry. And then they all show this nice Fano line shape. And that's because there's a continuum underneath. And this continuum has been shown to be from this longitudinal mode. Longitudinal mode is also sometimes referred to as amplitude or Higgs mode. So this appears in the AG symmetry because we are distorting the lattice uniformly, and so you change this condensation energy of the magnetic moments. You can also see the magnon if you go for the B1G, but you can also see that in other systems. Okay, so two solid experiments showing evidence for soft moment. So where does that bring us? Lead us to. So what we wanted to do with RIXS was to try to find evidence that would support the excitonic model by looking at the higher energy orbital excitations. So here's one of the first results that we collected with the instrument. This was taken with a resolution that was 1 eV. This means that the reason for this bad resolution is because we didn't have a high resolution monochromator. But it was fun to do this kind of measurement. So we scanned the incoming energy across the ruthenium L3-edge. And when you hit the atomic resonance, you will see energy losses appearing. And the lowest one is called A, and this is what we are mostly interested in. There's another one called B here, and that has to do with the EG states that are not really, they're actually something that we're not looking at. And then you have charge transfer at higher energies. So this A is what we would like to focus on. The experiment that we're going to be doing is to rotate the crystal. So we come in with photons with pi polarization, and we look at photons coming out with fixed angle, 90 degrees, and we look at both polarizations. And when you rotate the crystal, you change the momentum transfer in the plane. And you also change the polarization with respect to the crystallographic axis. So we improved the resolution by a factor of 10. And what you see is that A is actually multiple features. So A1, 2, 3, and 4 appearing here.
Sorry, Hlynur, yeah. Sean, do you have a question?
Yeah. So can I ask a question right here? Go ahead. Okay, so if I look at your structure on the left-hand side, the oxygen ruthenium plane, so what happens in a real sample where you're bound to going to have some oxygen vacancies and some oxygen interstitials? Do those guys contribute in any way to the magnetism in the system?
Yes, I believe they do. I think magnetism in calcium 214 is very fragile. There has, for instance, been work, I think it was titanium doped 214. And it was hard to see the longitudinal mode in that data. There's also.
I'm thinking to oxygen. Oxygen does not. Oxygen does not contribute to the magnetism, does it?
If you remove oxygen or put vacancies, then you change the valence on or the doping, and that would affect magnetism. The transition would be at different temperature, and that's what I think. Yes.
Okay.
So that's why there's always a lot of effort in getting clean samples. Okay, so we have these 4 multiplets appearing, and that's actually quite exciting because then you can start to think about the on-site interactions in the system. So are they actually do they have the right strength to support the excitonic magnetism? And we're going to be interested in Xi, which is spin-orbit coupling, delta, which is the tetragonal distortion. I mentioned to you that these octahedra are very squeezed, and squeezing it is an important factor in creating this magnetism. And then, of course, they have Hund's-rule coupling. So there are 3 models that have really been considered, or 2 for 214. The first one that has been dominating is the fact that, or takes the stance where spin-orbit coupling is weak and this tetragonal distortion is much bigger. So if delta is large, then you have fully occupied XY orbitals and then half occupied XZ and YZ. And this, I believe, is just orbital selective mod state. So gap would open up here. And like I said, it's fairly recently been discussed. The other extreme is if spin-orbit coupling is very large and delta is small. But the problem there is your system is non-magnetic, right? And I've showed you that this system has magnetic order. So you can kind of rule this out. It's interesting to note that this is where the poor iridates belong to, the double perovskites. And they have a stronger spin-orbit coupling, so this is larger, and so they stay non-magnetic. It's hard to get this J1 state lower. So for our model, we're going to take this stance in between, which is that spin-orbit coupling and delta are actually comparable. And just like in one of those cartoons that I showed you, you will eventually get magnetic moment appearing because J1 mixes with J0. So this is one of the best data set for this resolution that we had. So all of the features are more or less the same intensity. I've tried to fit them here with some curves, and then the bars are coming from the ionic model. These are calculations that were not done by me, but I'm gladly going to describe them. So here is the model, or the multiplets that we get from the ionic model. And if you just look, and this is plotted as a function of the ratio delta over E. And remember that the cases on the previous slide, we're all dealing with different ratios. So if delta is vanishing, then you get a non-magnetic state. This is the J0, 1, and 2. And if you start to crank up delta, then eventually you get something that resembles what we are seeing. So you have the A1 feature here. You have the broad A2, which is coming from many, many lines. And then you have the split at A3 and A4 here at higher energy. And this is kind of interesting. So A1 is simply the magnon plus the amplitude mode. Can also be referred to as the Higgs mode. A2 is an excitation it's an excitation, orbital excitation into the J equals 2 state. And then we have the center of this is, A3 and 4 are coming from spin state transition. So this is going from S1 to S0. And it's going to cost you a lot of energy. And that energy is determined by twice the Hund's-rule coupling. And then as you crank up delta, then these 2 states are splitting. So you can really just look at the data, and that will tell you what the tetragonal distortion is in the system. So the parameters that we get is 250 MeV, and the other one is 130. So we believe this is actually, these are fine parameters to support the excitonic model. Okay, so is this model any good? And I'm going to show you an example, what happens when you go into a cubic state where delta is 0. So we have a case here, potassium, ruthenium chloride 6. And this is, I believe, like the double perovskite iridites that have no magnetism, or should have. So susceptibility is flat in this system. So this is this, I think it's called Van Vleck susceptibility. And the multiplets in this compound would be determined by, because delta is 0, so psi is much larger. So you have, this is the spin state transition here, this S equals 0. And then S equals 1 and L equals 1 transforms into J2, J1, and J0. And they don't get split further because delta is 0. So this was interesting because, okay, here's some materials that we can actually use to confirm this picture. And this is the RIXS spectra that we collected. We took multiple momentum transfer. You can see, I mean, it's not really important, but this is shown here in the brilliance zone. The high energy spin state transition feature is actually not 2 peaks anymore, but more or less 1 peak appearing here. We have the J equals 2 excitation, not at 320, but somewhere closer to 200. And then we have a new one appearing here, which we believe is the J equals 1. And this is the state that would, in 214, would have been involved in the magnetism, but it's not in this case. So you can extract some parameters here, but the point is that we have an example of the end member of the excitonic model, which is, the non-magnetic version. Okay, so the question is, does the excitonic model extend to the bilayer? And so here's a spectrum that the RIXS spectrum that we collected on both systems, 214 and 327. And remember, the 327 is metallic and has a different magnetic order. So high energy looks similar, but the low energy one is very different. So instead of sharp multiplets that you get in 214, you have an asymmetric peak that has a peak position that is even larger than J equals 2. Okay, we can also notice that the magnetic excitation is at a different point. So this is data that is taken in the same condition and at the same momentum transfer. So there's a lot of things we can pick up with the RIXS in terms of different ground states. So this is kind of difficult because you cannot use the ionic model to extract parameters here. So there's a broad feature and there's probably a lot of peaks underneath, so we avoided to do that. But you can imagine that maybe you have these kind of transitions, but they are all mixing very nicely with the electron hole continuum, and you get this asymmetric feature instead. So what's interesting in 327 is that if you go from the magnetically ordered state into the paramagnetic state, the quasi-elastic line shoots up. So it has a finite energy here, and then it goes to 0. And this is just coming from strong ferromagnetic fluctuations in 327. So we can pick that up. So since we're not able to model this with the ionic model, we are left with the magnon, and that's what we did. So here's the magnon dispersion in 327. And unlike 214, it is actually dispersing outward from gamma. So you can see it's the 0 here, and then it goes towards the highest energy at the brilliance zone. And what we were able to do in this case was that we could overlay this data with what we were able to collect with neutrons. So the neutron data of the magnon is shown here in the blue. It could not go to high energy losses because the magnon was too weak for it to be detected. But you can see that's not the case here with RIXS. We can map out the whole dispersion relation here. So this is mostly just to show you that both neutrons and X-rays are actually quite complementary to each other. So this is where they work nicely together. So here is also clearly seen the difference in magnetism between 214 and 327, you can see that there's a big gap in 214 at gamma, but a small one in 327. And I told you that the gap was coming from tetragonal distortions, and they are smaller in 327, so this is going to be weaker. So this is kind of the link between the structure and magnetism. Okay, so I also mentioned to you that we can push this bilayer system into an insulator with titanium doping. And so here is data comparing 214 to the magnetically ordered titanium doped calcium 327. And you can see the picture is much nicer here. So the things are resembling each other. We have the J equals 2 states, they're lower in the titanium doped. And you have the spin state transition. It's not two separated peaks, but there is something here around the same energy. So this is nice. So it seems like what we're able to do is to push the system towards the excitonic model. If you go into the paramagnetic state of 327, the titanium doped, then it looks more or less identical to the paramagnetic state in calcium 327. So both have the strong ferromagnetic fluctuations. It's not clear to us why 327 is actually so sensitive to titanium doping. So this is 1%. It shouldn't do anything, but it does a lot. So we can apply the ionic model to the titanium doped 327, and what can help us is actually the structural data. So what I'm plotting here is the ruthenium 06, so the octahedral compression. In 214, it is largest. It is weak in 327, but in the titanium doped, this compression is sizable. So what we do then is to use the same parameters for spin-orbit coupling and Hund's rule coupling. We take them from 214, and we just plot the multiplets as a function of delta. And then we believe that the titanium doped 327 is located on the left side of 214, and that would bring this J equals 2 state towards lower energy. It will bring the spin state transition closer and potentially just forming this blob instead. Now, I think there have been no, at least published results on soft magnetic moment in titanium doped 327. But our RIXS results certainly are encouraging and seem to suggest that the excitonic model is also applicable in this case. Okay, so I'm done with the perovskites. How am I doing on time? Okay.
Yeah, you're good.
Yeah.
I mean,
so I'm going to spend the remaining of the talk on the Kitaev material, ruthenium trichloride, which I think you are all more familiar with. So Kitaev model is based on the D5 plus spin-orbit coupling, and you've probably seen this picture many, many times. You have the T to G forming J effective 1/2 and 3/2. They're split. You get this exotic wave function that is almost cubic. And then sometimes you can have trigonal distortions that would cause 3/2 to get splitted and mixed even into the J 1/2. Okay, then you get an insulator if this is a narrow band, and you have small u that can open up a gap. Okay, and if you have this kind of configuration, you put it on a honeycomblattice with edge shared octahedra, you can get Kitaev interactions, and this is what we are going to be looking at. So there are a lot of materials that are candidate for this kind of physics. The first one, I believe, was sodium 2 iridium 03 by Jokas and Philip. Later they did lithium 213, but both compounds order magnetically, so they are not spin liquids. Now, there's also work on what some people call the second generation of Kitaev materials. These are I think it's lithium 213 that has been replaced. So the layer of lithium has been replaced by hydrogen. And I think, Kemp, you've done the silver, right?
Yeah, we're working on the silver, but it comes from Fazal, our other friend from Toronto.
Yeah. And I think these materials it's not clear if there's spin liquid ground state or not, but certainly the magnetic order disappears. I mentioned to you cobaltates might be a good venue to look at. You do D7 high spin state, and this is something that came from our theory group. And then there's also, I think, the F electron materials. Okay, so the candidate that we're going to be looking at is ruthenium trichloride. It grows in the same crystal structure as the sodium 213, the iridate. What's interesting or nice about this compound is that it's fairly easy to grow. So you can see the crystal is about 5 millimeter in size, and then it can cleave. So you can make these monolayers of ruthenium trichloride, and with that reasonably size too, it keeps on getting bigger as well. You can make devices, right? You can gate it, or you can bend it, or you can use this kind of twisting tricks. So this field is very exciting, actually. So ruthenium trichloride is just like the other potential Kitaev materials. It orders magnetically, and this was shown by our colleague, my actually old coworker, Jennifer. Orders at 7 Kelvin in the same zigzag order as the sodium iridate. Jennifer has also shown that the magnetic moment is not in the plane, but is pointing with an angle of 35 degrees. And this is something that is important later on. You can use that to determine the coupling constants. Now, not all is bleak in ruthenium trichloride. Actually, one of the first experiments that came out that showed that this had something more to do with Kitaev magnetism was done by my friend Luke when he was in Toronto, where they look at the Raman scattering. They see a continuum. Here are phonons, and you wouldn't expect the continuum to appear in Raman scattering if you have an insulator. So there are no charge degrees of freedom. And in fact, you would only expect maybe magnons because it's magnetically ordered. But instead, you have a continuum that seems to survive up to high temperatures. Okay, so this was taken as a signature for fractionalized excitations. I think this data from Oak Ridge is nice. It shows that there are actually magnons in the system, but there's also this big continuum that appears and is present above the Néel temperature. And here is the important result. If you take a cut in momentum space, you will see that it has a star shape, and the biggest intensity is actually at gamma. And this is something that has been the focus of research for some time. So where is this intensity coming from? And we're going to be trying to address that in the next slides. Okay, so we decided to look into this compound because we were interested in refining the Hamiltonian for the system. It's obviously it's not just a Kitaev term because it has magnetic order. You also need more than just Heisenberg because you get this zigzag order, and so you add some other terms to it. So just to show you how difficult it is to determine these coupling constants, you can see here the phase or global phase diagram that was done by my old coworker, Jeff. So what he has done here is just to parameterize J, K, and gamma. And you can see that zigzag order appears over a quite a range of parameters. Spin liquid is only at these poles or here. So you can have, for instance, the Kitaev term K can be both antiferromagnetic or ferromagnetic in this model. So, it's important to actually try to do as good as you can to refine or find what these parameters are. So our goal is to find K, J, and gamma and make sure that we have the correct zigzag order. We have the correct direction of the moment, so this tilting of 35. And we can replicate this strange intensity at gamma that neutrons saw. Okay, so experiment is similar to the perovskites. We have the hexagonal perpendicular to the scattering plane. We come in with pi and we look at both polarizations, and then we just rotate the crystal and we keep things fixed at 90 degrees. We're going to be looking at the atomic multiplets, just like in the perovskites, and then we're going to use the momentum transfer that we have with tender X-rays to look at the low energy excitations here by cutting through either H0 or H8 direction. And you can see we're cutting through we're either going along the arms of the star or in between the arms of the star here. Okay, so just a few words on the multiplets. This is from 0 to 4 eV. We have a large excitation here at high energy that is coming from the EG, and it's all I can say here is it's fairly well described with the ionic model. We have a single excitation at low energy called A1 that is coming from this J3½ to 1½ excitation, and we can also get that with the ionic model. And we get some values for spin-orbit coupling that is quite consistent with what's in the literature. Okay, so we're going to be focusing the remaining of the talk on this low energy feature here. So here's data collected at our lowest temperature, 20 Kelvin at that time. And we are cutting along H0 or H8's direction. So there are two important things here. The first one is that we have a resolution limited quasi-elastic line. It's not at 0, it's at a finite energy. But A1 is broad, and it's broadened by about 50 MeV. And people are inclined to look at this broadening as coming from trigonal distortions. Okay, and this was actually shown very well in sodium iridate, where you have two peaks. And I think, Kemp, you've seen this in the silver compound, like it's two very well separated peaks. But it's kind of tricky to do it when you can't really resolve them, because as a function of momentum, the width is actually changing. And you can see here that the gamma, there's even a new feature appearing, this exciton that comes also in the iridates. So it's a bit tricky to determine splitting based on broadening. We determined the trigonal distortion in this compound based on magnetic susceptibility. And we believe this is elongation of so we're not pushing the octahedra. And we think this is something like 50 MeV, minus 50 MeV. And this is still smaller than spin-orbit coupling. So we're fine with this picture that I showed you in the beginning. The second important thing here from this data is coming from this enhanced intensity, right? And that's what we're searching for. We want this enhanced gamma intensity that neutron were able to see. So it's low here, but high at gamma. So we're going to be just integrating this whole area as a functional momentum, and that's what I'm going to show you here. Both the integrated intensity of J1½ and integrated intensity of A1. A1 is this orbital excitation. So this is uniform, right? It's more or less stable along H0, but it's slowly decreasing along HH. But the magnetic excitation is actually different, right? It peaks at gamma in both cases, and you can even see that it's narrower along HH, which is where we are going in between the arms of the star, and broader when we go along the stars here. So we're going to try to explain that with by choosing the correct parameters. But before we do that, it's kind of evident that you don't have any large intensity at the magnetic break peak here. So this means we're at 20 Kelvin. The Néel temperature is 7 Kelvin. So we're not that far above, but already there are no evidence for the zigzag order. So it's completely melted away. And this we want to capture with our parameters. So what we did was to ask Yuri Chalupka to do cluster calculations, and he came up with parameters that are again consistent with zigzag and the moment direction. And what's important here, and which I'll show is different from other models, is that the Heisenberg term is larger. So the ratio between J and K is larger than what has previously been discussed. They're both ferromagnetic, okay, and that has also implications. So this is the data from the calculation of the line, and you can see that if we were able to go to low temperature, 5 Kelvin, and this is something that is challenging to do experimentally, you would see the intensity from the magnetic break peaks. But the model tells you that even at 20 Kelvin, this intensity has quickly moved to the gamma point. It's gone. And this is simply coming from, this is showing us that the parameters are actually giving a very weak zigzag order. And in fact, intensity at gamma is coming from ferromagnetic correlation. And so we think that there's a ferromagnetic ground state that is very close to the zigzag order in ruthenium trichloride. So we can compare it to other models, and I just picked here two of them. One is coming from Jennifer's paper on the magnetic moment, and the other one is, I think, from Rosa Valenti's group. So we all have the same sign of K and J, but the difference is the ratio between K and J. So you can imagine that this ferromagnetic phase is less strong in the two models here. So the calculation would show you that even at 20 Kelvin, if you had the other two models, you would see an intensity at the magnetic Bragg peak, which is not what we see here. So our model is highlighting this fragility of the zigzag structure. This is nicely shown here. So you can see what would happen to the quasi-elastic scattering at 5 Kelvin. And even at 5 Kelvin, you would have intensity at gamma point. And this is very different from sodium iridate. So here's data that was taken 6 years ago, where you go above the Néel temperature, is 12, you go to 17, and you see this short range order here, but you see no intensity at gamma. And you even go to 70 Kelvin and you would see these peaks here. But in ruthenium trichloride, everything is washed out at even 50 or 20 or 50 Kelvin. Okay, so let me just show you some things that we would like to take this. So we have a method to probe the exchanges in ruthenium trichloride, and we can look at magnetism. And so a natural way for us would be to look at these nanoflakes and even heterostructure. And we've proven that you can look at compounds. So here's the RIXS data taken on bulk. We have RIXS data taken on 70 nanometer thick flakes, and we've even looked at 10 nanometer here. So this is quite an exciting field for us to go towards. So you can start to actually manipulate these the magnetic ground state. Okay, so here's a summary. So I hopefully convinced you that we're able to look for candidates for the excitonic magnetism in ruthenium perovskites. What we would like to do next is to be able to look at the magnos with higher resolution, and that's something we're actually working on. And then we've done some very nice work on the quasi-elastic scattering, the momentum dependence in ruthenium trichloride. And in combination with cluster calculations, you can try to extract, we extract actually the coupling constants in this compound, and nanosheets and so forth. Okay, and I'd just like to end by acknowledging the people that have been very important for this project. The RIXS instrument was actually started by Hassan Yavas, who was at PO1, but has since 3 years ago moved to US and is now working at SLAC. We have been working closely with Beamline PO9 when Jennifer was there as a postdoc, and then we work with the Beamline scientist there, Sonia. And then from the group of Max Planck Institute Stuttgart, it's obviously supported by Bernard Keimer. The experiments were done by Joel Bertenshaw and Hakuto Suzuki. The crystals were grown by Max, the perovskites, and the ruthenium trichloride through the group of Bettina Lodge. And then calculations, obviously, by Giniat and Yuri Chaluka. Okay, so I'm sorry that I went 10 minutes over time, but I'd just like to thank you for your attention. And I'll gladly take some questions if you have.
All right, thanks, Hlynur. I think your timing is actually fine. We can be a little bit flexible too with this remote mode.
Yeah.
Okay, we have some questions. Sean, you have a question. You have your hand raised.
So it looks like, from your talk, it appears to me that the dream of having a Kitaev quantum spin liquid in ruthenium trichloride is finished. Is that right from your talk?
To get I actually thought there are some interesting things that happen in magnetic field. So that's something that I didn't even. Yeah.
No, if you go back to a slide on, say, 5 Kelvin, this slide.
Yeah.
It looks like you have a ferromagnetic state at 5 Kelvin.
Yeah.
So then it's impossible to have a quantum spin liquid, isn't it?
I don't know. I mean, this ferromagnetic order is coming from the Kitaev term and the Heisenberg term, and this is just what happens in the model. If you want to get a spin liquid, I don't. I mean, yeah, you'd have to reduce the J term somehow.
It's Sean. It's the dream is maybe still there. It was known since ruthenium chloride was discovered that it orders magnetically. So in zero field, it was never a quantum spin liquid. But as Hlynur said, this interesting result happens in kind of reasonably large magnetic fields of about 7 Tesla, where something happens to the magnetic order. But yeah, but maybe Hlynur, you can do something interesting with the nanoflakes.
Yeah, so that's where you can. That's where we believe we can try to push things around, right? You can change the bonding angles and so forth more easily. But to do that, I mean, if you want to do the nanoflakes, you need to be able to probe your system somehow, and that's what we're trying actively to do it with RIXS.
Okay. Do I understand correctly that the broadening in the energy dispersion curve means the curve has to be a Lorentzian, not a Gaussian, right? And where you said that the broadening was due to the distortion, then that means if it's due to a distortion, don't you see a splitting of the peak rather than broadening?
We don't. No. There are similar results done with the ruthenium M match, and you can do that at, for instance, NSLS2, and they have a better resolution, but they still only see one single peak. So splitting has not been observed.
Okay.
I mean, it depends, Sean, on the strength of the splitting compared to the instrumental resolution as well. Right, the instrumental resolution, I mean, I don't know what it is on RIXS, Hlynur, but typically it's like almost a Gaussian. So.
Yeah.
Wait and see if there's questions.
Can I ask a question?
Oh, yeah. Go ahead.
In the Perovskite, I think it's known that there's a function of its strain. You can also drive the metal insulator transition. Strain can drive the 214 into a metallic state. I was wondering if you explored that on RIXS too.
We did an experiment not with strain but with electric field. And,
right.
I'm not sure if I get this correctly, but I think the story in calcium 214 with field was heating, but I'm not sure. Yeah, so we tried. Yeah.
No, I was going to say in that compound, I've seen videos of as a function of electric field, you can actually see the crystal breathing. Visually, the size of the crystal changes with the field because you're driving the structural transition. So I was just wondering if you can also see that in RIXS or how that affects the DD excitations.
Yeah, so we tried it with electric field, but we did. I think we went not very far. We did manage to go into a metallic state, but not the metallic state that you have without a field, which has different structure.
I see.
So within that measurement, we didn't see a big change in the DD. But I have to admit, we didn't do this very carefully, though. Regarding your strain, I mean, there are these amazing strain devices that you can use. We haven't tried it on calcium 214, though.
Okay, thank you.
And I'm not sure. So I think the paper that you were referring to, it was from Switzerland, right?
Felix Bamberger has this.
He reaches some amazing strain, right? With just a mechanical screw, or.
Yeah. And I know. I mean, Felix is my PI, my PhD supervisor. So I know even the glue, the epoxy itself, will actually just drive that strain.
Yes,
as a function of cooling.
Yes, I think that strain goes beyond what you can do with piezo devices.
I see.
But it was interesting. Yes, yes, you can get the metallic state.
Yeah.
But
Okay,
we've done 2 and 4 with above the MIT, and then it's completely different. So I would expect to see a very different thing.
I see.
I guess I'll ask a question. I know you said it's a mystery as to the mechanism of what happens with the small titanium doping in 214.
Yeah.
Do you have any, like, what are your guesses as to what's going on? Because it's quite a strong effect for such a small.
It's strange because it's strange because if you look at the distortions.
Yeah.
If you believe, I mean, I think this is data from powder neutron diffraction.
It's powder neutron? Okay.
Yeah. So there's not much difference in the compression in the paramagnetic state of 327 and paramagnetic state of titanium dope 327. So it's not like you are squeezing the lattice, I think, already, right? If you were to do that, then maybe you would see a difference even at room temperature. So if I were to guess, I mean, this has more to do with magnetism than the structure. But
there's a structural transition.
There's a structural transition here that causes a big jump in the compression. This is similar to what happens in 214, but not to the same extent. The crystal doesn't shatter, for instance. But yeah, so there is a structural transition, but I mean, they look identical then in the paramagnetic state. So yeah, I'm still trying to think of it. If you have a good idea, then you can let me know.
Yeah, that one is quite weird.
It's also, I mean, you get the metal insular transition is also quite low. I mean, it's not like I don't know.
Yeah, this one seems interesting. We'll see if there's more questions. I have some like technical questions for you, so I'll wait a second and then I'll just probably stop the recording because those are probably boring for the recording.
Can I ask a real dumb question?
Go ahead.
Can you explain to me why Hund's rule doesn't work for oxygen in the structure in a solid phase?
I mean, oxygen is fully occupied. No.
You can have a let's say if oxygen for some reason gets popped out from the site and it becomes an ion, but it's stuck inside the lattice.
Yeah.
And then so it's not fully occupied. Does the Hund's rule work on that ion?
So would the oxygen then have magnetic moment? Is that?
Yes, that's the question. Yes.
But what is the oxygen? What?
Just let's say oxygen 1 minus.
I don't think that exists.
Why?
Oxygen 1 minus?
Yes.
It's not chemically stable.
Yeah, well, it's stuck in. You can imagine there's some charge in the lattice, right? No.
No, I think it will just pull. It will just get rid of that electron.
Why? Try to avoid the Hund's rule.
Sorry, I don't know how to answer this. Difficult question.
I know it's a dumb question.
Sorry.
I'm just wondering if I can definitely stick an oxygen inside the aluminum metal, right?
Mm-hmm.
And then I'm sure that oxygen impurity would be charged, would gain some electrons, right? Not all, may not be the all 2 electrons. Let's say in oxide, in the iron oxide. Well, okay, so in iron oxide, it's actually the iron so that's not a fair question. I guess it's something that chemically that can compete with the ability of oxygen to steal electron. I'm just wondering, is it possible at all to have a magnetic moment on oxygen impurity in solids in general?
Yeah. Yes. Yes, it is. Yes.
In which system?
I think people even talk about this in a sense as happening in cuprates, because those compounds are maybe a little less in the strongly correlated regime and maybe a little bit more in the covalent regime. Mm-hmm. So the electrons can live a little bit on the oxygen and a little bit on the copper, or on the copper site. So you can have. But I think the compounds here Hlynur is talking about are really kind of mod insulators. Well, okay, the insulating ones are. So you kind of think of them as like in the atomic limit, and you think of charge as being isolated on each site. But I guess that is just a cartoon. So.
Okay. Thank you.